Hello. All right, in this section, we're going to keep going in Chapter 8. We're going to look at surfaces of revolution. So this stuff depends really heavily on what we just did in Section 8.1, so make sure you're all caught up in 8.1 before you try this stuff. All right, let's get started. So what is a surface of revolution? Well, the idea is it's just a curve rotated about a line, or it's the lateral boundary of the solids that we computed back in Chapter 5. Right, so here's a cylinder, for example. Like, how do you compute just like the outside of it? Well, think of it like a soup label on a can. If you just cut the label and open it up, well, it's a rectangle, so it just has an area. When it's on a surface, we call it surface area. But really, we're kind of imagining that we could cut it open and spread it out, right? So, we can see that this can has a height h, and because the circumference is 2 pi r, when you unroll it, the length across it is 2 pi r, the height is h, so it's a rectangle, 2 pi r times h. So that's the idea. We want to look at what happens when we unroll these things. What do we get? So the next type of surface we want to look at is a cone. What does it look like to take a cone, slice it, and press it open? What does it look like? So if the cone has base radius r, then this circle is pi r squared. So when we cut it and open it up, that rounded part at the bottom will be 2 pi r. The length of the cone is L. So again, when you cut it and open it up, you get L. Now the way we compute theta is you just set up a ratio, right? It's a proportion basically, right? It's saying that this whole outside part is 2 pi r, and then you divide it by L. So it tells you how much, because remember, this is fixed based on r. If r is a constant, this is fixed. So if L is smaller, when you press the cone open, it'll go farther around. If L is bigger, when you press the cone open, it's not as, it doesn't open up as much. So we're defining theta to be just the ratio of 2 pi r divided by L in radians. And then we know that the area of a sector of a circle with radius L and angle theta is 1/2 L squared theta. So this is a geometric fact you learned a long time ago. It should make sense though, right? Because if L is the radius, right, the area is pi r squared, right? But that's for a whole circle. We're saying that we're only going around theta. We're only going around theta units. So if you go all the way around 2 pi, then it makes sense that the formula is 1/2 r squared, and then theta would just be 2 pi, right? Because you get pi r squared. So because this function, the area as a function of theta is linear, and obviously you need to square the radius because it's a circle. So what we do is we just plug all of this stuff that we've already computed into the formula. So the area is 1/2 L squared theta, but we know theta is 2 pi r over L, and everything simplifies. You just get pi r L, which is pretty interesting, right? So the area here has nothing to do with theta, right? It's just a function of r and L, which is what we want. Because when we're talking about cones, you don't see theta, right? You don't see theta until you cut it and press it open. So we've managed to get theta out of the equation, which makes everything we're going to do so much easier. And what we're going to be doing in this section is we're going to be looking at when you have like a cone stacked on top of another cone, what is the area of that little band that's left over? So just imagine you take a cone and stack it on top of one, and there's like a little bit extra around the bottom. What's the area of that? That's what we need to find out. All right, and then what if we have things more complicated than cylinders or cones? So we're going to follow the strategy we did with arc length, right? This is the picture I had from the arc length video. What you do is you have this polygonal path, And the idea is that we're going to rotate this whole thing around the x-axis. And instead of getting a curvy surface like a vase or something, you get these little bands that are basically big cone minus little cone, each of these bands. And so what we can do is we can sum up the areas of all the bands and take the limit as n goes to infinity to get more bands. And we'll call that limit an integral. And it actually works out really, really nice, as you will see. Right, so here's what we're going to use. I just talked about this, but here's what we're going to use. So each of these bands, again, think of it as an area. We don't care about the volume of this thing. If you take a line segment at an angle and rotate it, you get a band, which is a piece of a cone minus another piece of a cone. So we're going to look at the surface area of this thing, which is the surface area of the big cone minus the surface area of the little cone. Right, so that's all we're doing. So remember, the surface area of a cone is pi RL. So pi is a constant. So let's look at the big cone. Well, the big cone's radius is R2. The big cone's length is L1 plus just L. So it's pi R2 L1 plus L. Then we subtract the smaller cone, which has radius R1 and length L1. So minus pi R1 L1. Then we rearrange this equation so that we get numbers times L. And this is kind of what you'd imagine it to look like, right? Here's the big radius times L. Here's the difference in the smaller radiuses times L1. That's kind of what you would expect. So we're going to revisit that formula in a second, but we got a lot of work to do before we do that. So we're going to set up similar triangles and get a ratio. So just to show you where we're at, we're just talking about these triangles here. This triangle and this triangle. Right? So corresponding side lengths of similar triangles have the same ratio. So L1 over R1 is the same as L1 plus L over R2 because they're similar triangles. Then we basically cross multiply and rearrange. I skipped some of the algebra there. If you're interested, go ahead and do the algebra on your own. Because what I want to do is get this whole thing in terms of this. So we take this whole thing and just plug in this. And it works out really, really nice. So the area is just the sum of the radiuses times just that little bit of the length. Remember, L is just that little bit. So that works out really, really nice. We got a lot of those variables to kind of go away. So now we're going to define a new radius, R. We're just going to call it the average radius of the band. So we just take the small radius and the big radius and we average them, right? Add them up, divide by 2. So that means 2R, just multiply both sides by 2, right? So 2R is R1 plus R2. And then put this whole thing into here. And you get this amazing, very simple formula. And it should be a little bit surprising, right? That if you have one cone that has length L, it's just pi RL for the area. When you have two cones stacked together and you subtract the little one from the big one, and you call the difference L, it's 2 pi RL. So all the algebra works out really nice. So that's the formula we're going to use. And here is sort of more about how we do it. So we found the area of these little bands. These individual bands are 2 pi RL, right? And what we're calling L is the length. Well, the length of these little bands is just, it's just the distance formula between pi minus 1 and pi. And that should look familiar because that's exactly what we did in section 8.1 when we approximated those things using distances. So we're just going to make a bunch of bands and rotate it around the surface. And it turns out that it works out exactly the way you would expect it to. That the area we've already sorry, this distance here, so this length is what we called arc length. And then when you go around, you're just multiplying by the circumference, which is just 2 pi x or 2 pi y, as you will see, because we're using this formula, right? So here, r is the radius. So if we're going in the y direction, it's y. If we're going in the x direction, it's x. And L is that length. So we already know what L is, right? L is that distance formula for the little piece here. This is L. And that's R. So we're going to do the same thing we did in previous sections. Take AB, divide it into equal subintervals. And then we're going to use the exact same argument from section 8.1. That if we let yi, so that's just the y coordinate of the function at some point, and the part of the surface, we approximate it with the line segment, and we rotate the line segment to get the band. The slant height L is exactly the distance formula for the little band, and we know the average radius, and we already know the surface area. We've already computed this. So all we do is we take this surface area and plug in this formula for R. And plug in this for L, which we already did, right? So here, this becomes this, R becomes this, simplify, and apply the mean value theorem, just like we did in section 8.1. We're just saying that there is some number xi star. And the trick here is that as we take the limit, as n goes to infinity, the bands get smaller. Both endpoints get closer to this. And so we're just going to essentially replace both xi and xi minus 1 with xi star. And that's what this part is explaining. So if this seems a little hand-wavy, if this seems a little non-rigorous, it's based on stuff you did in Chapter 4 in Calc 1, where you were doing Riemann sums. A lot of that looks like this. If you recall, when you first did Riemann sums, you could, remember we said you can pick any point in an interval in order to do a Riemann sum. They were called sample points. We're doing the same thing here. We're just picking any point. But we're choosing the point so that the point that we pick has this nice feature. And the feature, we're interested in is that that as n causes delta x to get very small, so as n goes to infinity, this would be like the left end. I'm sorry, this would be the right endpoint gets closer to f of xi star. The left endpoint gets closer to xi star. So we're basically squeezing the function as n goes to infinity. And what that lets us do is take this ugly function and replace both of these things with f of xi star. Right? So the 2 pi stays. Then we have 1/2. This becomes f of xi star. This becomes f of xi star. We're just saying that the upper and lower endpoints are getting closer to this number that the mean value theorem predicts. So a number plus itself just makes 2 of them. So the 1/2 and the 2 cancel, and you're left with just f of xi star. And this whole thing just becomes delta x. Right? It's the whole radical, right? So it's 2 pi. This is the radius. F of xi star is the radius. And then this is the distance formula that we showed in section 8.1. So one complete revolution would be approximately this. And we just take the Riemann sums and you sum all of these things. Right? So we're talking about individual bands, but when you sum all of them, we're saying there's n bands. As n goes to infinity, the Riemann sum turns into a definite integral, and it turns into this. So there should be no surprise here that here's the formula for the arc length, and this is the formula for the circumference. And that should make sense, right? That's the way we defined cylinders earlier, right? It's just, you take the equation of like the line segment and you rotate it, and it's 2 pi r. So this is actually the formula that we're going to use. Again, must have a continuous derivative, just like we had in section 8.1. And you can write it either way. You can write it with f of x, you can write it with y, dy dx. And this is, again, if we're going in the y equals f of x, so we're given it y is a function of x, you choose it this way. If you're given x as a function of y, you go the other way. Just like we did in chapter 5 and in here in chapter 8 so far. So the formulas you're going to use look like one of these, or again, you could go in the y direction. And of course, there are differential versions of the formulas as well. Here where you see ds, it's the same ds we saw in section 8.1. So ds is just defined by this, either dx dy or dy dx. So depends on what axis you go around, which formula you choose. And it depends on how this is defined that tells you how to do the derivative. All right, so let's see some examples of this. It looks a lot like surface area. I'm sorry. It looks a lot like arc length from 8.1. All the calculations look really similar. All right, so we're going to set one up but not evaluate it, just so you can see how to construct these things. And then we're going to show how to compute this thing going around the x-axis or the y-axis. So we're given y as a function of x. So we use the dy dx form. Which axis we go around tells us which of these to use. Right? Do we use y? Do we use x? And you'll see when we get into it, after I show you the example, you'll see how to choose which formula to use. All right, so first thing we do, of course, is the derivative, right? Always. Right, so our function is x e to the minus x. You guys know how to do derivatives or you wouldn't be this far in this class. I'm going to go ahead and simplify it, just because I don't like having a bunch of negatives floating around if I'm going to square something. Remember, this goes into this formula to square it. This is the ds right here. Well, it's part of the ds, right? It doesn't have the dx or dy, but so this is just like the arc length part of it. So I'm just plugging this thing in here, and then I simplify it a little bit, mostly because if you look at this horrible formula, there's no way to solve this in an integral. We just can't do it. So you'd end up doing this on your calculator anyway, and I'd rather type this into my calculator than that. So there's the arc length. There's the arc length part here. This is the ds. And then notice we're going 2 pi y. So this whole thing is ds. Why are we doing 2 pi y? Well, it has to do with the way that we're going around the axes. So you pick this x or y depending on what the radius is going to be. So here we're going around the x-axis. Right? We're rotating around the x-axis. So the height, right, the radius of that rotation is measured in y. So we got to use y here. And then we're going to replace it with the function, right? So our original function is y equals x e to the x. So you plug the function in there. And then you plug the ds part in here. And we're given that the integral goes from 1 to 4. So just plug in 1 to 4. And you're done. Again, you would do this on your calculator. You would not want to do this integral by hand. It would be absolutely horrible. And it might not even be possible to do it by hand, as we saw in chapter 7. But you don't have to evaluate it. Just set it up, simplify it. And so this is the kind of thing, you have to do this a little bit on the homework, but on a test. The algebra, as you're going to see in the next 2 examples, some of this algebra gets really, really complicated. Make sure you're practicing just setting these things up. On a test, I'm very likely to ask just a setup problem so I don't have to grade a bunch of algebra. Now, what if we're going around the y-axis? Well, the arc length we've already computed, right? So that doesn't change. But the circumference, the radius of the circumference is measured in the x direction. So we put the x here instead. This time you don't have to replace it with a function because everything else is in terms of x. So you're done. So really the only 2 differences here, so the arc length is the same. Here we have to put the function in because the change in the radius is a function of x. Here, the change in the radius in the y direction is just x. So setting up problems in this section is really similar to what we did in Chapter 5. If you didn't do particularly well on the exam that covered Chapter 5, make sure you're putting the time in to set these up. These questions can be asked a lot of different ways, and you don't even have to have problems where you can do the integral, because we can do it on our calculators. All right, let's keep going. And I'm going to drink some coffee. All right, so here we have x as a function of y. So we have to use the other form. And we're told y-axis. Right? So the way this is given to us tells us how to compute ds. How this is given to us tells us which formula to use. Do we put a y in the formula or an x in the formula? Right? Here we're going around the y-axis, so we're going to plug in x, but x is really a function of y. So we're actually, when we're ready to do the substitution, we actually plug this back in. All right, first step, as always, is a derivative. Here, because x is a function of y, I don't recommend using the prime notation. Write it as dx dy. And of course, you get a chain rule here, and it simplifies real nice to this. Make sure you can get all the intermediate steps on your own. This problem has an a in it, so we can't do it on our calculators. So we have to do it all the way through. So there's the ds formula. Just plug it in. And the next step, we're going to need a common denominator. So do this part first. The negative goes away. Here you get a y squared. This whole thing squares out. We're going to need that common denominator. So we have a squared minus y squared plus y squared. So the y squareds go away. We saw a problem similar to this earlier in 8.1. And you just want to keep simplifying. You do not have to write plus or minus. A is a number. It is not a function. And it doesn't matter if it's negative. It just becomes positive. Right? So this thing simplifies like this. So I can't simplify this any farther, so I just leave it. And then I'm going to plug this into the surface area formula. So this is my ds. And I'm going to choose dy because I was given the function as a x as a function of y. So we choose the dy version of the formula. And we're going from c to d, that's in the y direction, 2 pi x, right? We're going around the y-axis. So the circumference is measured in x units, but x is a function of y, so I need to replace this with my function. I already computed dx dy. Just plug everything in. So we're going from 0 to a over 3. The 2 pi stays 2 pi. Here is my x as a function of y. Here's what I just computed. Right, this whole thing reduced to this. But I'm not done. It does simplify nicely, but you got to stay with it. This radical and this radical cancel. I pull the 2 pi to the front, so I just get a dy from 0 to a over 3. So the integral of a dy is just ay from 0 to a over 3. And you're done. So you never know ahead of time if these problems are going to work out nicely or not. You are counting on stuff to cancel. Sometimes stuff cancels in good ways, other times bad ways. Sometimes it cancels nicely, sometimes it doesn't. You just really have to pay attention. Make sure you're going back over, how to set these up. Is it X or Y? Is it around the X-axis or around the Y-axis? Lots of considerations. So if you're given X as a function of Y, you choose the dy version of the formula. So it's going to go from C to D, and then you're going to have the ds is in the dy direction. But the 2 pi X or Y depends on what axis you're going around. So if it's Y as a function of X, and you put an X here, it stays an X. But if it's X as a function of Y, when you put an X here, you've got to replace it with the function. because these all have to be y's or you can't do the integral. When you're ready to do the integral, you can't mix x's and y's. It has to be all x or all y. Okay, so now we're going to see sort of a wacky problem that looks fairly easy, but you're going to see that you have to make a lot of choices along the way. Some of the choices can help you, some of them can hurt you. I already know how to do the problem, so I always try to look at problems like this through the eyes of somebody learning it. Make sure you understand step by step what I'm doing. When you are done with this problem, make sure that anything you don't understand, you can go look up how to do it, because you're going to have to be able to do problems like this on the homework, possibly on a test. Okay, so we have an infinite curve. We want to find the surface area of an infinite length curve. And I know what you're thinking. You're thinking, well, if it's an infinite curve, it's going to have infinite surface area. But we know that that's not true, right? We've seen problems in Chapter 7 where the area under an infinite curve is finite. So the length and the area are not necessarily related in any nice way, right? They're related through these complicated formulas, right? First step, as always, is take the derivative. Now here we're going around the x-axis, and we were given y as a function of x. So that tells us which formula to use. So when I do the ds, I'm going to use the dx version of the ds. That's hard to say. And when I build my formula, it's going to be 2 pi y. And then I'm going to replace y with that function of x. So there's my ds. So you just plug in the derivative. Pretty easy stuff. Simplify it as much as you can, because here we have to do the integral. So you always simplify these things as much as you can. Now, I'm just going to, so here's my whole formula, right? My ds is a dx, and it's 2 pi y because I'm going around the x-axis. So circumference, the radius is measured in y units. But I have to replace y with the original function, which I'm going to do. I'm going to pull the 2 pi to the front, which I did. And it's an improper integral from 0 to infinity. And at this point, you have a lot of choices. So this is the way I chose to do it. If the the solution manual and the like the book version of how to solve this, I don't like at all. I think my version's a lot better. So again, if you're getting tutoring help or whatever with this kind of stuff, you're sort of on your own. I would recommend doing it the way I'm going to show you to do it. Okay, this is an improper integral, so I go ahead and just do the improper integral. Next step, we're going to look at how to do this integral. So I looked at it and I said, if you look on your table of integrals, so I think it's number 30. Yeah, no, it's number 21. So number 21, I was looking at it because you're allowed to use these integral tables to do homework. And as you know, on tests, I will provide these tables. You look at this and you say, I want it to be a squared plus u squared. And you're looking at this and you're like, well, what am I going to make a and what am I going to make u? Well, I'd much rather have a be 1 and u be whatever the square root of this is. The reason is, when we do a u substitution, you have to compute du's. You don't want a bunch of fractions and negatives floating around in your du's. So I looked at this and I said, I'm going to make u, so here's the function again. I said, I'm going to make u equal to 2e to the minus 2x. So what I did is, there was a 2 pi out here. I actually pulled the 2 back in. Normally, you just keep constants to the front, but this is going to help me avoid a lot of fractions. Any fractions I get, I can keep pulling them to the front. I don't want fractions inside radicals and stuff like that. It's just too confusing. So yeah, my u is 2e to the minus 2x. When I compute du, you get minus 4e to the minus 2x. And we don't have a minus 4e to the negative 2x here. We have a 2e to the minus 2x. So just multiply by negative 1/2 on both sides. So this whole thing, 2e to the minus 2x dx, I'm just going to replace with negative 1/2 du. This whole thing, I'm just going to replace with 1 plus u squared. Right? So 1 plus u squared, negative 1/2 du. So it's starting to simplify. What happens here, though, is you have to change the limits. And there's a lot of ways to look at this. In the interest of not skipping steps, I'm going to show all the steps here. So you have to change these limits from x to u. So you just plug in the lower limit, plug in the upper limit. And then I distribute the negatives, and the negative 1/2 I distributed and pulled it to the front. So I have square root of 1 plus u squared du. This lower limit, e to the 0 power is 1. 2 times 1 is 2. And this, I just leave it alone. I can't simplify it, so I just leave it alone. In the next step is a choice I made, and I think you should do it. You might be thinking, I can evaluate this right now because it's no longer an improper integral. That is correct. It is no longer an improper integral. And when you think about what happens when you plug infinity into here, you're not allowed to plug infinity into limits, but so I'm not going to backtrack. So that's why I'm doing it this way. If you plug in infinity, e to the minus infinity power is 0. So 2 times 0 is 0. So this number is going to be smaller than this number. So what I'm going to do in the next step is I'm going to flip those limits and get rid of that negative. I just don't like negatives. You know, oh, this should be pi over 2. Sorry, this should be pi over 2. I'll fix that when I post it. So this, all it did is get rid of the negative. This is still pi over 2. Yeah, there it is. Now I just do the integral. So you look up the integral on the table, or we've seen in chapter 6 how to do these kind of integrals. It's a trig substitution. So you can do the trig substitution if you want, but it's also number 21 on the table. So I just plug everything in. And again, pi over 2 out front, not pi over 2. So I'm done. Now I just have to evaluate. And when you plug in 2 as the upper limit and 2e to the minus 2b, you get this horrible, awful thing. I distributed the pi over 2. And the limit doesn't apply to this because these are numbers. So I just move the limit all the way to, things that contain b. And then if you look at it, these are all numbers. So this thing's going to simplify to something. What happens when I plug infinity in here? Every single one of these things becomes 0 when I plug it in. So here all I did is simplify, and I pulled that pi over 2 back out front. This whole thing simplifies to this. All of these little things are 0. So this is 0. This is 0. Because natural log of 1 is 0. So this whole thing, all that stuff with the limits, b going to infinity, all becomes 0. The only thing that matters is this left side. And you're done. So I like my way of solving it. I mean, it might have looked horrible to you as an audience, but to me, this didn't seem so bad because I'm keeping the numbers out of the integrals. I'd rather have b's in here than a bunch of numbers. Because when it's time to evaluate it, I can just look at this and say, this is 0, this is 0, this is 0. I'm not trying to do calculations. None of this stuff required any calculations. It's all just 0. And to me, that was easier than doing it any number of other ways. So make sure you can do this problem. This is it's a long problem and it's involved, but it's something you should be able to do. And in fact, in Calc 2, you must be able to do, actually. All right, well, that's it for this video. If you got any questions, let me know. And that's it for Chapter 8. Next video you see will be Chapter 9. Have a good day, and I'll see you next video. Bye-bye.